According to defense industry reports, engineers on a test range in the American Southwest watched a tungsten projectile the size of a fence post leave a square-barreled launcher at over 5 times the speed of sound. Seconds later, a reinforced concrete bunker built to survive a direct bomb hit ceased to exist. There was no explosive flash, no fuel-air fireball, just kinetic energy converted to thermal force so intense that the target simply vaporized. The program that reportedly fired it is known as Thor, and it is designed to do what no bomb has ever done: make the underground world above ground. The weapon itself sits on a heavy military chassis that can roll across desert roads and rough terrain alike. The launcher isn't a conventional artillery tube. It's a square-barreled electromagnetic rail system that accelerates projectiles using electrical force instead of chemical propellants. The barrel is long enough that the launcher extends across most of the vehicle's length, and the recoil gets absorbed by a hydraulic system that keeps the truck stable for repeated shots. The entire platform is mobile and difficult to spot from the air. The Thor hammer has not been confirmed by the Pentagon as a single-name program, but every technology required to build it is already being tested by the United States military. The name Thor is not an accident. It traces directly back to a weapons concept first imagined in the late 1950s by Jerry Pournelle, then a Boeing operations researcher who would later become one of the most influential science fiction writers of the Cold War. Pournelle envisioned telephone pole-sized tungsten rods dropped from orbit, striking the Earth with the kind of velocity that defined the extinction of the dinosaurs. He called the concept Project Thor. The Pentagon called it something else entirely. Others simply called it rods from God. That was nearly 70 years ago, but a weapon built on these principles wouldn't need orbit. It would just need a highway, a power supply, and a target that somebody thought was safe underground. The hardest problem in modern warfare hasn't changed in decades. It's the target buried deep underground. North Korea hides missile launchers inside mountains. Iran built centrifuge halls beneath dozens of feet of reinforced concrete and compacted earth. Terrorist networks have learned that a cave or a tunnel is often more survivable than any above-ground fortress. For the United States and its allies, these deeply buried targets represent an asymmetrical threat that can't be answered with diplomacy and can't always be reached with conventional force. The Pentagon's historical answer has been to build progressively larger bombs. The Moab was detonated against ISIS positions in Afghanistan. The 30,000-pound MOP punches through hardened layers before exploding deep inside. In 2025, President Trump claimed that MOP-class weapons had obliterated 3 underground nuclear sites in Iran, protected by military-grade concrete. Whether those strikes achieve full destruction remains classified, but the logic behind them is public knowledge. The deeper a target is buried, the bigger the bomb required to reach it. There's a practical ceiling to that logic. Bombs large enough to threaten deeply buried bunkers become so heavy that only a handful of aircraft can carry them. They need time to reach their target and create blast signatures visible for miles, and they carry the political and environmental cost of high explosives, which means collateral damage, civilian risk, and the possibility of fallout or secondary fires that extend well beyond the intended strike zone. The Earth has always won this arms race because there's no theoretical limit to how deep a determined adversary can dig, but there's a very real limit to how large a practical bomb can be. The Thor hammer takes a different path entirely. Instead of more explosives, it uses more speed. The physics are almost elementary, but the engineering is brutal. Kinetic energy equals 1/2 mass multiplied by velocity squared. That squared term is what matters. Double the mass of a projectile and you double its energy. Double the velocity and you quadruple it. A pickup truck moving at highway speed carries a certain amount of kinetic energy. A baseball moving at the same speed carries almost none. But reverse them, fire that baseball at Mach 5, and the math flips. That's why a tungsten rod weighing less than 100 pounds traveling at hypersonic velocity can deliver more destructive force at the point of impact than a conventional explosive warhead many times its weight. Tungsten is chosen for a reason beyond its density. At hypersonic impact velocities, the projectile doesn't merely punch through a target. The leading edge of the rod encounters resistance so extreme that the metal itself begins to behave like a fluid. The rod penetrates concrete and steel by converting into a superheated plasma jet that bores a narrow channel through whatever stands in its path. The penetrator length plays a decisive role. A modern kinetic energy penetrator can't typically penetrate deeper than its own length, but within that depth, the destruction is absolute. The heat and spalling generated by the penetrator passing through armor, and the shock front that develops behind it, destroy the target from the inside out without ever requiring a chemical detonation. In 2013, researchers from the Air Force 846 Test Squadron and Lawrence Livermore National Laboratory proved this was not theoretical. They test-fired a tungsten-rich kinetic energy projectile on a specialized track at Holloman Air Force Base in New Mexico. The shell moved at 3,500 feet per second, more than 3 times the speed of sound. Matt Weingart, a weapons program development manager at Lawrence Livermore, described the difference between conventional and kinetic warheads with precision. The classic approach packs chemical explosive into a container and lets the blast wave do the damage. The kinetic approach arrives at the target already carrying the energy needed to destroy it. As Weingart explained, the more mass you can move at that speed, the more violence you deliver. Army Major General William Hicks put it more directly at a defense summit in 2017. He compared a wide-area kinetic strike to a big shotgun shell. Not much can survive it. A crew inside a main battle tank might live, but the vehicle becomes non-mission capable. Everything below that level of protection is dead. The elegance of the kinetic energy projectile is that its yield isn't a fixed explosive charge. It's a function of velocity and density. Military planners can adjust the effect by adjusting the projectile, not by swapping warheads. Pornell's original vision was orbital. He imagined a satellite magazine loaded with 20-foot tungsten rods, each controlled by a directional thrust system that could deorbit a rod on command and drop it onto any point on Earth within minutes. The concept was studied seriously. The 2003 United States Air Force Transformation Flight Plan included a proposal called hypervelocity rod bundles. The specifications were staggering. Each rod would be 20 feet long and 1 foot in diameter. It would impact at Mach 10, carrying energy equivalent to roughly 11.5 tons of TNT. The mass of a single rod would exceed 9 tons. The advantages were real. With 6 to 8 satellites in the right orbits, a target anywhere on Earth could be struck within 12 to 15 minutes. There would be no missile launch warning. The infrared signature would appear in orbit, at no fixed position, and with a magnitude far smaller than an intercontinental ballistic missile. The rods would be difficult to track and nearly impossible to intercept at those closing velocities. But orbital kinetic weapons carry political, legal, and practical problems that have kept them on the drawing board for 70 years. Positioning ammunition in orbit is astronomically expensive. The Outer Space Treaty creates legal complications. And perhaps most importantly, an orbital strike platform is a strategic asset that can't be hidden. Once the satellites are launched, every nation with a telescope knows where they are. The Thor hammer brings the same physics down to a truck. The electromagnetic railgun is the critical bridge. The United States Navy pursued railgun technology for years before shelving the program amid technical hurdles and budget pressure. Then, in early 2026, the Navy quietly resumed railgun tests at White Sands Missile Range, deep in the New Mexico desert. General Atomics is now pushing a new generation of electromagnetic weapons capable of firing hypersonic tungsten pellet payloads with 32 megajoule muzzle energy. The completed system is expected to launch shells at up to 4,500 miles per hour, 6 times the speed of sound, with enough force to blast through 7 steel plates in sequence. The Army is running parallel experiments. The hypervelocity projectile program, originally developed as ammunition for the Navy railgun, is now being test-fired from conventional Army 155mm howitzers. In June of 2025, the destroyer USS Jason Dunham tested BAE Systems' hypervelocity projectiles as part of a fleet counter-drone trial. The Army intends to spend roughly 3 years studying the physics of firing these rounds from standard artillery tubes. The logic is clear. If a howitzer can fire a tungsten round at hypersonic speeds, a larger dedicated launcher on a heavier chassis can do far more. The Thor hammer is the logical escalation: a longer barrel, a larger bore, a dedicated mobile platform with the electrical generation capacity to power repeated shots. It doesn't need to reach orbit, it just needs to reach the target. What happens at the moment of impact isn't an explosion in the traditional sense, it's a phase change. When the tungsten rod strikes reinforced concrete at hypersonic velocity, the front surface of the projectile experiences pressures measured in millions of pounds per square inch. The concrete doesn't crack, it doesn't spall in large chunks. The nose of the rod converts to plasma, and that plasma jet bores through the target material like a cutting torch moving at Mach 5. The channel is narrow, often only inches across, but it is deep, and the material inside that channel isn't displaced, it's transformed. The pressure wave that follows the plasma jet propagates through the internal structure of a bunker, with effects that can collapse walls, sever power conduits, and destroy equipment even when the penetrator itself doesn't physically touch every surface. The overpressure inside a sealed underground facility can rupture lungs, burst eardrums, and disable personnel without a single fragment or flame. Against a hardened target, the effect is surgical. Against a softer target, it is annihilation. There's no fallout because there's no fissile material. There's no chemical residue because there's no chemical explosive. There's no fuel-air fireball because the energy release is too fast and too focused to create a sustained combustion zone. What remains is a narrow borehole through yards of hardened concrete and steel, surrounded by a zone of thermally compromised material that has been flash heated to the point of structural failure. The target has been vaporized in the literal sense that a portion of its mass has transitioned directly from solid to gas under the thermal load of impact. Compare that to a traditional bunker buster. The Moab, at 21,000 pounds, creates a blast radius measured in hundreds of yards. It requires a cargo aircraft, a clear drop zone, and favorable weather. The 30,000-pound MOP needs a B-2 Spirit bomber and a precise release point to achieve the correct impact angle. Both leave signatures that are visible from space. Both risk collateral damage measured in city blocks. The Thor hammer leaves a hole, and the truck that fired it can be 20 miles down the road before the dust settles. A weapon that can vaporize buried bunkers from a moving truck is not the kind of capability you advertise on the evening news. The Pentagon hasn't announced the Thor hammer from a podium, and that silence is part of the design. The United States maintains a category of weapons development known as Special Access Programs. These are black projects formally defined as unacknowledged programs that aren't publicly acknowledged by the government, military personnel, or defense contractors. The Pentagon's black budget has historically run into tens of billions of dollars annually. In 2021, General John Hyten, then the vice chairman of the Joint Chiefs of Staff, pushed to declassify an existing space weapon, specifically because the strategic value of some capabilities depends on adversaries knowing they exist. Kinetic weapons don't follow that logic. The value of the Thor hammer isn't deterrence through visibility, it's deterrence through uncertainty. If an adversary knows with certainty that the United States possesses an orbital rod from God's system, they can plan around it. They can time their movements to avoid predictable satellite windows. They can invest in anti-satellite weapons. They can calculate the cost of the system and judge whether the United States would actually use it in a limited conflict. But a truck-mounted launcher that can appear on a highway, fire a round through a mountain, and disappear into traffic isn't something an adversary can plan against. It's not something they can track from orbit, and it's not something they can deter with their own space weapons. The secrecy also serves a tactical purpose. Every underground command center, every buried missile silo, every tunnel network in the world is designed to survive a specific class of threat. Iranian centrifuge halls are built to withstand the massive ordnance penetrator. North Korean tunnels are deep enough to ride out conventional airstrikes, but none of them were engineered to survive a tungsten rod moving at hypersonic speed from a launcher that doesn't exist on any known order of battle. If the Thor hammer is real, every one of those facilities is now a little less safe, and the adversary doesn't know which ones the United States can reach or when. The F-117 flew in secret for years before the public ever saw its shape. The B-21 Raider is flying now with classified capabilities. The Thor hammer fits that lineage. A weapon that could rewrite the physics of bunker busting wouldn't need a press release. It would just need a target. The Thor hammer isn't an isolated program. It's the convergence of three technology lines that have been advancing independently for 2 decades. The first line is the projectile itself. Tungsten penetrators have grown denser, more precisely machined, and more aerodynamically stable as manufacturing techniques have improved. The second line is the launcher. Electromagnetic railguns were a Navy curiosity in the 2000s, a failed program in the 2020s, and a revived priority in 2026. The third line is mobility. Truck-mounted artillery systems from Rheinmetall, Hanwha, and others have proven that heavy-caliber weapons don't need tracked vehicles or fixed emplacements. A launcher on a heavy truck chassis can relocate faster than counter-battery radar can track it. Combine those three lines and the future of ground-based kinetic weapons becomes clear. Autonomous targeting systems fed by satellite imagery could spot a buried facility, calculate firing coordinates, and relay them to a Thor hammer launcher in a convoy hundreds of miles away. AI-assisted fire control could adjust for wind, temperature, and atmospheric density in real time, improving accuracy until a single round is sufficient. The launcher could fire, retract its barrel, and drive to a new firing position before the first impact echo returns. The arms race underground would shift. Nations that have invested billions in buried command centers, tunnel networks, and hardened silos would face a new calculus. Digging deeper is always possible, but every additional foot of depth requires exponentially more concrete, more time, and more money. At some point, the cost of burying a facility exceeds the cost of firing a tungsten rod at it. That is the moment when underground warfare becomes obsolete. The United States has spent 70 years trying to solve the bunker problem with bigger bombs. The Thor hammer suggests that the answer was never bigger. It was faster. If realized, the Thor hammer would prove that the most terrifying weapons don't need nuclear material or chemical explosives. They just need speed, mass, and a truck that can aim at anything buried deep underground. The United States created a weapon so strong, it doesn't need explosives, just raw speed and metal. The Navy's over $200 million railgun fires solid steel at over 8,000 feet per second, tearing through ships like paper from nearly 100 miles away. But after years of jaw-dropping tests, this terrifying machine vanished. Why did the Navy suddenly shut down its most powerful weapon? And what secret danger forced them to walk away? Join us as the United States tests its railgun worth millions. The metal beast sits motionless on the testing platform, its twin rails gleaming under the harsh lights of the Naval Surface Warfare Center. This is no ordinary weapon. The electromagnetic railgun represents 15 years of military engineering and $500 million in taxpayer money. Its sleek barrel stretches forward like a cannon from the future. But inside, pure science replaces gunpowder and explosives. When the countdown reaches 0, invisible forces unleash their fury. Electromagnetic fields, generated by massive electrical currents, grab hold of a 7-pound projectile and accelerate it down those parallel rails. The speed builds instantly, faster than any traditional bullet, faster than most missiles. In less than a second, the projectile screams out of the barrel at 8,270 feet per second. That's more than 5 times faster than a rifle bullet. The destructive mathematics is terrifying. This projectile carries no explosives, no warhead, and no chemical energy. It doesn't need them. At hypersonic speeds, kinetic energy becomes the weapon. The faster something moves, the more devastating its impact. When a 7-pound chunk of metal strikes a target at these velocities, it delivers the same destructive force as a small artillery shell packed with high explosives. Navy engineers pushed their creation even further during years of testing. Early demonstrations showcased an 8-megajoule system firing projectiles with incredible precision. But the real monster was still coming, a planned 64-megajoule weapon system designed specifically for warships. The power requirements were staggering. Each shot would demand the same electrical energy that powers several city blocks. The weapon's range capabilities redefine naval warfare possibilities. Traditional ship cannons reach maybe 15 miles on a good day. The railgun could strike targets 100 miles away with pinpoint accuracy. Enemy ships, coastal installations, even aircraft, nothing within that massive radius would be safe from this electromagnetic hammer. Testing footage reveals the weapon's raw power. Each firing sequence begins with a low hum as capacitors charge with millions of volts. Then comes the moment of release, a brilliant flash, a thunderous crack, and the projectile vanishes into the distance faster than the human eye can track. The ocean becomes the only safe backdrop for these demonstrations. No military installation dares test this weapon anywhere near populated areas. The implications terrified and excited military planners in equal measure. Ships equipped with railguns could engage multiple targets simultaneously without worrying about ammunition storage or explosive safety. Traditional naval guns require tons of volatile gunpowder stored deep within a ship's hull, a floating bomb waiting for enemy fire to ignite it. Railguns eliminate that vulnerability. But the electromagnetic monster demanded a price that even the world's most powerful navy couldn't pay. The electrical requirements pushed ship power systems beyond their limits. Each shot drained enough energy to power a small town. The rails themselves wore out after relatively few firings, requiring constant replacement and maintenance. Heat buildup threatened to melt the weapon's core components. By 2021, reality overtook ambition. The Navy quietly shifted funding away from railgun development, focusing instead on hypersonic missiles and laser weapons. The electromagnetic beast that once promised to revolutionize naval combat became a $500 million lesson in the gap between theoretical possibility and practical deployment. But while America's electromagnetic dreams crumbled, another science fiction weapon was quietly proving its deadly potential. Could invisible beams of light become the Navy's ultimate defense? The USS Portland cuts through Pacific waters on May 16, 2020, its crew preparing for a test that would make naval history. High above the ship, a small drone buzzes through the morning air, unaware it's about to become the target of humanity's first operational laser weapon system at sea. The laser weapon system demonstrator sits mounted on the ship's deck, like a sleek telescope pointed at the sky. Inside its housing, solid-state laser diodes generate an invisible beam of concentrated light energy. Unlike the railgun's brute force approach, this weapon kills with precision and silence. No projectiles, no explosions, no ammunition to reload, just pure energy traveling at the speed of light. The targeting sequence begins as radar operators lock onto the drone's position. Computer systems calculate flight path, speed, and distance in milliseconds. The laser weapon swivels smoothly, tracking its target with mechanical precision. Then comes the moment that changes everything. The invisible beam reaches out across the sky and touches the drone. What happens next defies traditional warfare expectations. The drone doesn't explode in a dramatic fireball. Instead, its electronic systems simply die. Critical components overheat and fail as the laser's energy overwhelms delicate circuits. Within seconds, the unmanned aircraft tumbles from the sky like a broken toy, its threat neutralized without a single conventional weapon fired. The successful test sends shockwaves through military circles worldwide. For decades, science fiction promised laser weapons that could defend ships from incoming threats. The Portland's demonstration proves that the future has arrived. The solid-state laser system can engage multiple targets simultaneously, switching between threats faster than any human gunner could track them. Navy officials released carefully worded statements about the test's success, but the implications speak louder than any press release. Enemy drones, small boats, and even incoming missiles now face a defensive system that operates at light speed. Traditional countermeasures become useless against a weapon that strikes instantly across vast distances. The laser's versatility extends far beyond anti-aircraft duties. Small attack boats, the kind used by terrorist organizations and rogue nations, become sitting ducks against this technology. The beam can disable engines, destroy navigation equipment, or blind optical sensors without sinking the vessel entirely. This precision offers military commanders options beyond total destruction. Power requirements for laser weapons remain significant, but manageable compared to railguns. Modern warships generate enough electricity to operate these systems continuously without draining other critical functions. Heat management poses challenges, but engineers have developed cooling systems that keep the lasers operational during extended engagements. The cost advantages become clear quickly. Each laser shot costs roughly $1 in electricity. Compare that to million-dollar interceptor missiles traditionally used against aerial threats. A single laser weapon system can engage hundreds of targets for the price of one conventional missile intercept. International observers watch these developments with growing concern. Laser weapons represent a fundamental shift in naval power projection. Nations without access to this technology face obsolete fleets overnight. The balance of power at sea tilts decisively toward countries possessing these light-speed weapons. Military strategists recognize the broader implications immediately. Swarm attacks using dozens of cheap drones could previously overwhelm ship defenses through sheer numbers. Laser weapons flip that equation completely. Now expensive attack platforms become vulnerable to relatively inexpensive defensive systems that never run out of ammunition. While laser beams defend ships with light-speed precision, the Navy's most devastating weapons still rely on raw explosive power. But what happens when these 1,000-pound instruments of destruction need reloading in the middle of a battle? Deep in the missile compartments of Navy destroyers, ordnance crews prepare weapons that can reach targets over 1,000 miles away. The Tomahawk land attack missile sits secured in its vertical launch cell, a sleek white cylinder packed with enough explosive power to level city blocks. These cruise missiles represent the ultimate expression of long-range naval striking power. Each Tomahawk carries a sophisticated guidance system that uses terrain contour matching to navigate across vast distances. The missile flies low, hugging the Earth's surface to avoid enemy radar detection. Its jet engine pushes the weapon at subsonic speeds for hours, following pre-programmed routes loaded before launch. The Tomahawk's 1,000-mile reach transforms naval warfare strategy completely. Enemy targets that once felt safe hundreds of miles inland now face destruction from ships positioned far beyond the horizon. Coastal installations, command bunkers, and critical infrastructure all fall within this weapon's deadly embrace. 7 different variants of the missile provide commanders with options ranging from conventional explosives to specialized warheads designed for specific target types. Beneath the surface, submarines carry their own arsenal of destruction. The Mark 54 torpedo weighs over 1,000 pounds and packs enough Torpex explosive to crack a submarine's hull like an eggshell. Torpex, short for torpedo explosive, delivers 50% more destructive power than traditional TNT. These underwater assassins can track enemy submarines across distances of 10,000 yards, their sonar guidance systems hunting prey through the ocean depths. Surface vessels launch these torpedoes from deck-mounted tubes, sending them racing through the water at speeds that give enemy submarines little time to react or escape. The Mark 54's advanced guidance system can distinguish between different types of underwater targets, ensuring it strikes the intended vessel rather than friendly forces operating in the same area. But the Navy's most dangerous moment comes not during combat, but during the deadly process of rearming these weapons at sea. In calm harbors, massive cranes lift 1,000-pound missiles into their launch cells with mechanical precision. At sea, however, the ocean's constant motion turns this routine operation into a life-threatening gamble. Waves roll beneath the ship's hull, causing the deck to pitch and sway unpredictably. Sailors must guide missiles weighing more than half a ton into narrow launch tubes while fighting against gravity and momentum. One wrong move, one moment of lost concentration, and crushing death becomes inevitable. The Navy removed shipboard cranes years ago after too many accidents proved the danger too great to accept. Today's tensions with Russia and China make at-sea rearming operations more likely than ever before. Extended deployments in contested waters mean ships may need to reload their weapons far from friendly ports. Ordnance crews train constantly for these scenarios, knowing their lives depend on perfect execution under impossible conditions. The process begins in darkness to avoid enemy observation. Sailors wearing safety harnesses work in teams, using hand signals to communicate over the noise of wind and waves. Each missile must be lifted by human strength and mechanical winches, guided carefully into position while the ship rolls beneath their feet. Modern missiles like the Norwegian Naval Strike Missile add another layer of complexity to rearming operations. These weapons can engage both ships and land targets at ranges up to 345 miles. But their sophisticated electronics make them extremely sensitive to shock and impact during handling. Even with these devastating long-range weapons loaded and ready, enemy missiles can still penetrate deep into battle zones. So what happens when hostile projectiles break through and target the ships themselves? Modern naval warfare operates on a simple principle. Multiple layers of defense must work together, or the ship dies. When enemy missiles streak toward American warships at supersonic speeds, commanders have only minutes to deploy countermeasures that mean the difference between survival and destruction. The first line of defense begins hundreds of miles from the target ship. Norwegian naval strike missiles, mounted on Allied vessels, reach out across 345 miles of ocean to eliminate enemy launch platforms before they can fire. These precision weapons use advanced guidance systems to track moving targets across vast distances, striking enemy ships with devastating accuracy. Each naval strike missile carries enough explosive power to cripple or sink most enemy vessels with a single hit. The weapon's sophisticated targeting system can distinguish between different ship types, prioritizing high-value targets like aircraft carriers and command vessels. When multiple missiles launch simultaneously, they coordinate their attacks to overwhelm enemy defenses through synchronized strikes. As threats move closer, the second defensive layer activates. HIMARS rocket systems, traditionally designed for land-based artillery, have been adapted for ship-to-shore bombardment operations. These versatile launchers can fire multiple types of projectiles, from precision-guided rockets to long-range tactical missiles. The M142 high-mobility artillery rocket system proves its worth when enemy forces attempt amphibious landings or coastal bombardment. Each HIMARS pod contains 6 guided rockets or larger tactical missiles capable of striking targets with pinpoint accuracy. The system's rapid-fire capability allows ships to saturate enemy positions with devastating firepower in minutes. But the most critical moments come when enemy missiles penetrate these outer defenses and race toward their targets at speeds exceeding the sound barrier. Ship-based radar systems track incoming threats while computers calculate impact trajectories and engagement windows. Seconds count as the final layer of defense prepares to engage. The Phalanx close-in weapon system represents the last hope for survival. This automated defense system combines sophisticated radar tracking with a 6-barrel Gatling cannon capable of firing 4,500 rounds per minute. The weapon's nickname, Sea Whiz, comes from the distinctive buzzing sound its spinning barrels create during firing. Phalanx operates completely independently of human control once activated. Its radar dome rotates constantly, scanning for incoming threats within a 5-mile radius. When hostile missiles enter the engagement zone, the system locks on and unleashes a stream of 20mm tungsten projectiles designed to shred incoming warheads. The Gatling cannon's rate of fire creates a wall of metal in the sky. Each tungsten round travels fast enough to penetrate missile casings and detonate warheads safely away from the ship. The system can engage multiple targets simultaneously, switching between threats in milliseconds as its computer brain prioritizes the most dangerous incoming missiles. Engagement ranges remain deliberately short to avoid hitting friendly aircraft or missiles. The Phalanx fires only when enemy projectiles close to within 1 to 5 miles of the protected vessel. At these distances, the system has mere seconds to identify, track, and destroy threats before they impact. Modern anti-ship missiles travel at speeds that compress engagement windows to almost nothing. A missile flying at Mach 3 covers the Phalanx's maximum engagement range in less than 10 seconds. The automated system must detect, track, calculate, and fire without human intervention, relying entirely on computer processing power and mechanical precision. When ship-based defenses reach their limits, the ultimate response launches from carrier decks at supersonic speeds. But what happens when humanity's most advanced killing machines become too powerful for their creators to control? The flight deck of the U.S. Gerald R. Ford pulses with activity as red-suited ordnance crews prepare the deadliest aircraft ever deployed at sea. F-35 Lightning II fighters sit lined up like sleeping predators, their stealth profiles designed to slip past enemy radar undetected. These fifth-generation fighter jets represent the pinnacle of airborne warfare technology. Each F-35 costs over $100 million and carries sensors capable of detecting threats from hundreds of miles away. The aircraft's stealth coating absorbs radar waves, making it nearly invisible to enemy tracking systems until weapons release. Advanced computer systems process battlefield information faster than human pilots can comprehend, turning each jet into a flying supercomputer armed with precision munitions. The ordnance crews work with mechanical precision, their bright red uniforms making them instantly recognizable on the busy carrier deck. These specialists handle weapons that could level city blocks, loading guided bombs and air-to-air missiles onto aircraft with practiced efficiency. Each crew member trains for years to safely manage explosives, powerful enough to sink enemy warships or destroy hardened military installations. Modern naval aviation operates on a scale that dwarfs previous generations of warfare. A single F-35 can carry multiple precision-guided munitions, each capable of striking targets with surgical accuracy from distances exceeding 100 miles. The jet's internal weapons bay conceals these deadly payloads from enemy sensors, maintaining stealth characteristics throughout combat missions. The loading process reveals the raw, destructive potential these aircraft carry. Guided bombs weighing 2,000 pounds slide into internal weapon compartments, their guidance systems programmed to strike specific buildings or vehicles with pinpoint accuracy. Air-to-air missiles designed to destroy enemy fighters beyond visual range mount beneath the wings, their seekers calibrated to track heat signatures or radar emissions. Flight operations begin before dawn as pilots prepare for missions that could reshape global conflicts. The F-35's helmet-mounted display system projects targeting information directly onto the pilot's visor, allowing weapon engagement without traditional cockpit instruments. This integration of human and machine creates unprecedented combat effectiveness, but also raises disturbing questions about the direction of modern warfare. As these advanced weapons systems become more capable, military planners acknowledge growing concerns about their ultimate implications. The F-35 program alone costs over $400 billion, representing the most expensive weapon system in human history. Nations worldwide scramble to develop countermeasures for aircraft that outclass previous fighter generations by enormous margins. The rapid pace of military technological advancement accelerates each year. Weapons that seemed impossible a decade ago now deploy operationally across global conflict zones. Artificial intelligence integration promises even more dramatic capabilities, with autonomous systems beginning to make targeting decisions without human oversight. Naval aviation crews witness this evolution firsthand as new weapons arrive faster than training programs can adapt. Missiles with ranges exceeding 200 miles allow single aircraft to engage multiple targets simultaneously. Electronic warfare systems can disable entire enemy communication networks from hundreds of miles away. The destructive potential concentrated on modern carrier decks equals the firepower of entire armies from previous wars. This exponential growth in military capability creates paradoxical situations where even the operators express unease about their tools. Veteran pilots describe weapons so advanced that they fundamentally alter the nature of aerial combat. Young ordnance crews handle munitions powerful enough to trigger international incidents with single targeting mistakes. The psychological impact extends beyond military personnel to civilian populations worldwide. Nations without access to fifth-generation fighters face obsolete air forces overnight. Regional power balances shift dramatically as advanced weapon systems concentrate in the hands of technological superpowers. International observers watch these developments with mounting anxiety, recognizing that weapons designed for deterrence may eventually prove too tempting to leave unused. The hope remains that such devastating capabilities will never face full operational deployment, but history suggests otherwise. From drones to hypersonic missiles, today's battlefield is evolving faster than ever, and Germany isn't left behind. Conventional weapons still rule the front lines, like the MG3, which is a formidable weapon that was used to strike fear in Allied soldiers. It still dominates modern battlefields with its raw power and reliability. But as bullets continue to blaze, a new weapon silently emerges: lasers. Germany is investing heavily in directed energy weapons that strike at the speed of light. Could lasers render traditional guns obsolete? And are we ready for this next phase of combat? Join us as we unveil this Germany laser machine gun, which is way more advanced than you'd think. Modern military laser systems are proving to be more and more vital as warfare is increasingly fought in more technologically advanced ways. It is confirmed that laser systems can perform a variety of tasks, but they are mainly used to neutralize threatening targets. The systems are highly accurate and effective in taking out targets, specifically those that are unmanned, like drones. The big countries are in a race to get the best systems, and Germany has one of the best laser systems it uses to protect its land from unwanted aggression. But before we get into the beams, let's take a look at the greatest machine gun to ever grace the battlefield. For over 60 years, one German machine gun has stood as a benchmark of battlefield dominance, a mechanical symphony of speed, precision, and sheer durability. It's a weapon forged in war, hardened by time, and still trusted by militaries across the globe. But perhaps the most astonishing fact isn't its endurance or impact. It's that the man who designed it had never made a gun in his life. The story and basic design of the MG3 machine gun dates to the shadow of World War II. As Adolf Hitler prepared his people and pushed them towards the second global conflict he was about to trigger, the Wehrmacht needed a modern replacement for its aging MG34, a solid weapon, but too expensive and slow to produce. What they wanted was something faster, simpler, and utterly terrifying. And that challenge would fall into the hands of a man with zero weapons design experience. The Germans were the undisputed designers of machine gun technology, and they had proved how lethal their weapons could be during World War I when they were used proficiently to hold the Allies back and lock them in lengthy and excruciating trench warfare. However, the MG34 had some crucial drawbacks that Germany needed to correct. The machine gun was peculiarly sensitive to extreme weather conditions, dirt and mud, and its manufacturing process was complex and expensive. 3 companies were requisitioned in February of 1937 to present designs for a new generation of machine guns. Grossfuss AG of Döbeln, Rheinmetall-Borsig AG of Schummerda, and Stubgen AG of Erfurt. Grossfuss AG's design quickly stood out, employing a unique recoil-operated roller locking mechanism instead of the gas-actuated systems used by its 2 competitors. It would appear that people with no experience had quite the time during the World War, because astonishingly, and just like Hitler himself, the company had no earlier experience in weapons manufacture, mainly producing sheet metal lanterns before venturing to design a machine gun. Dr. Werner Gruner, one of its leading design engineers, had never worked with war weapons before he was assigned to the project. However, he was a resourceful man and an authority in mass production technologies. Eager to learn what he was getting into, Gruner joined a machine gunner's course to familiarize himself with the functionality and characteristics of said weapons. He also interviewed dozens of machine gun crews to learn about the needs and ideas that the end users had. Gruner implemented all this knowledge into a mass production system developed by the Mauser Rifle Company. The man who had never built a gun before was now ready to mass produce the most powerful machine gun in World War II. The novel weapon was made of pressed and stamped carbon steel metal with only the most essential parts milled from solid steel. The design also called for spot welding and riveting to connect components, decreasing the need for machining and high-grade steel alloys. As such, the manufacturing process used less strategic resources than its predecessor and was cheaper to produce. Gruner soon discovered that less is more when developing reliable and cheap machine guns, and reduced the time needed to complete the MG 42 to 75 man-hours, as opposed to the 150 man-hours required for the MG34. The new machine gun also required only 27.5 kilograms of raw materials instead of the 40 kilograms of the MG34, and the cost was reduced from 327 Reichsmarks to 250. The new design was purposely kept as similar as possible to the MG34 to maintain familiarity and compatibility with the various mounts and other accessories developed for the MG34 and its different combat roles. And initial trials immediately showed that the new weapon was at least as efficient as the old MG34 machine gun. While they were similar, some very significant changes made the new design superior. The saddle drum magazine feed option was dropped, leaving the gun to fire-belted ammunition or from a 50-round drum-shaped Gurt-Trommel belt container mounted to the gun's receiver. Also, the weapon's open sights were simplified to improve aiming. All these adjustments were intended to increase, maintain, or accommodate the gun's high rate of fire. Despite the simple and cheap materials used for the MG42, the machine gun turned out to be sturdier and more resistant to jamming than the MG34, making it much more friendly to dust, dirt, and unfavorable battlefield weather. The MG42 was massively deployed in 1942 and instantly became a hit, becoming much feared by the Allies. The Soviets even nicknamed it the Linoleum Ripper, and British and US troops called it Hitler's buzzsaw or Hitler's zipper. As it reached German soldiers' hands, the MG42 was the most advanced machine gun in the world, with almost twice the rate of fire of the Vickers and Browning machine guns. As tensions between the West and the Soviet Union rose after the war, West Germany was again allowed to rearm after years of prohibition. The West German forces knew that the MG42 was an excellent and reliable weapon and asked the US for permission to use it as their new machine gun. The US authorities responded that any machine gun they used would have to adhere to NATO ammunition standards. West Germany was left with two options: developing a machine gun from scratch or modifying the MG42 and transforming it into a NATO-compliant weapon. The decision was easy, and the new modified machine gun would be known as the MG1. Rheinmetall, the German company in charge of making the modifications, made several versions of the new machine gun rechambered to take 7.62 times 51mm NATO ammunition. The MGZ1, MG01A1, MG1A2, MG1A3, and MG2 all had the same core design as the MG42. Still, they included minor adjustments to make them more proficient in the post-World War II NATO scenario. Still, the most polished version was achieved in 1968, and it would be known as the MG3. Compared to the previous post-World War II MG machine guns, the MG3 features an improved ammunition feeding mechanism with a belt-retaining PAL to hold the belt up to the gun when the top cover plate is lifted. It was also equipped with an anti-aircraft sight and a new ammunition box that improved the performance of an already remarkable gun. The MG3 had evolved significantly from its predecessor, and its many future variants further refined its performance for specific roles. Still, at its core, the MG3 retains the backbone of the MG42, and most of its parts are freely interchangeable. During the late 1960s and early 1970s, the MG3 demonstrated to be an exceptional machine gun, and it was evaluated separately by numerous NATO nations, producing great reviews. Today, the weapon is used by 48 countries worldwide, including Germany, Canada, Australia, Italy, Spain, and Sweden. The MG3's 60-year design continues to provide a tremendous fire rate that can perform brilliantly even in the 21st century. It is so impressive that machine gun crews must undergo special training to avoid sustained fire at all costs. When fired in its bipod-mounted light machine gun role, the MG3 operators are trained to fire brief bursts of 3 to 5 rounds and attempt to optimize their aim between shots. Meanwhile, MG3 operators strive to fire bursts of 20 to 30 rounds when in its tripod-mounted medium machine gun role. After approximately 150 rounds of rapid fire, the MG3 crew will replace the hot barrel with a new cool one. If this procedure is not followed, the barrel becomes unusable. In addition, the crew members in charge of barrel replacement are equipped with protective asbestos gloves to prevent burn injuries to their hands. Military analysts still rate the MG3 among the top 3 machine guns in the world, along with the Soviet PKM and the Belgian M240 machine gun. Impressively, the MG3's original design is 20 years older than the PKM and almost 40 years older than the M240, and there are no signs of abandoning it anytime soon. But what if we told you Germany didn't stop there? Today, they're building weapons that don't just feel like lasers. They are lasers. One of the major players in this arena is, of course, the German military powerhouse Rheinmetall, responsible for a lineup of air defense systems, including Skynex, Sky Ranger, Skyguard, Sky Shield, and the Millennium Gun. These systems work harmoniously to offer armed forces a robust defense against adversaries. Let's start by focusing on the laser system. Other countries have already bought into the idea of a laser defense system. The USA has the ANSC-3 laser weapon system, Israel has the Drone Dome and Iron Beam. Germany is not left behind. Their equivalent system that they've designed is known as HEL, or High Energy Laser, designed by the country's engineering powerhouse, Rheinmetall. The laser has been a useful addition to the Rheinmetall Skyranger 38x8 vehicle to help with air defense. The high-energy laser weapon has its own sensors. This laser shoots a 20-kilowatt beam that can automatically lock onto targets and render them ineffective. There are exciting plans to increase the power of the laser as well. The immediate target for the German company is to increase this power to 50 kilowatts and eventually to 100 kilowatts in the near future. This will provide the laser with a very long reach, but also a practically unlimited supply of laser ammunition at a cost of only around $1 a shot, assuming power is available. Rheinmetall has actually managed to successfully test its new 50-kilowatt high-energy weapon. The test went through the whole operational sequence from target detection and tracking to target engagement. This was held at Rheinmetall's Ochsenboden Proving Ground in Switzerland. This was done in challenging, snowy conditions and blinding sunlight. The test proved a 5-fold increase in laser power available for the laser's use cases, which included air defense, counter-rocket, artillery, mortar, CRAM, and asymmetric warfare operations. Another plus from testing is that it proved the laser to be deadly accurate. It showed detection, pursuit, and successful engagement of an extremely small ballistic target measuring just 82 millimeters in diameter and traveling at approximately 50 meters per second. This was to simulate a mortar round. The fire control unit detected the target with no delay. This was then followed by mechanical tracking with a 30-kilowatt laser weapon station. The laser's weapon module took over tracking the target visually, which was then engaged and taken out in flight. The Skyranger itself has impressive capabilities. Its comprehensive sensor array enables automatic air monitoring, allowing the system to select the appropriate deterrent to address emerging threats promptly. Boasting a remarkable fire rate of 1,200 rounds per minute, the onboard 30mm x 173 KCE revolver gun stands as the world's top-performing weapon in its category. This ammunition is equipped with programmable time delay capabilities, enhancing accuracy against exceptionally small targets. Guided missiles grant the Skyranger heightened flexibility and extended range. Aside from the laser system, there are other aerial defense systems that demand attention. One of such is the Millennium Gun, which stands apart from the other air defense weapons. This distinction arises from the fact that this specific weapon is ship-mounted rather than land-based. However, similar to its counterparts, the Millennium Gun is produced by Oerlikon, a Swiss company that now falls under the ownership of Rheinmetall. At the heart of this gun is a remarkable 35mm automatic cannon, recognized for its extraordinary firing rate of 1,000 rounds per minute. This rapid-fire capability is coupled with exceptional precision. Another thing that sets the Millennium Gun apart is its utilization of Rheinmetall's pioneering AHEAD ammunition, a combination that makes it a formidable asset for any naval fleet. Moreover, the Millennium Gun can be seamlessly integrated with advanced sensors or incorporated into a broader command and control system, enhancing its efficacy as a cutting-edge weapon platform. Alternatively, it can operate independently with the addition of radar and optronic sensors as a self-contained close-in weapon system. This battle-proven system has garnered popularity among numerous nations. Following extensive rounds of technical, tactical, and sea trials, the Royal Danish Navy opted for this system across all of Denmark's Absalon-class combat and flexible support vessels. In addition, several South American and Eastern European navies have adopted the Millennium Gun to replace their existing 40mm and 75mm naval armaments. Let's transition back to land operations with the Skyguard system. Originally introduced in the 1960s as a replacement for the Swiss Air Force's outdated systems, this fire control system is now under the ownership of Rheinmetall. The initial development of Skyguard was a collaborative effort between Oerlikon and the United States Raytheon Company. The Swiss company focused on creating the Skyguard fire control system, which effectively manages twin 35mm cannons. Presently, Skyguard has advanced to its third iteration, and the interconnected Skyguard and Skyguard 3 fire units are built upon the original concept of layered defense. This comprehensive system comprises a fire controller, search radar unit, along with two twin-barrel 35mm cannons. Its global appeal is evident as it is currently employed by more than 40 countries worldwide. Now let's delve into Sky Shield, which essentially represents an enhancement of the Skyguard system. Developed by Oerlikon Contraves, Sky Shield is designed to provide defense against tactical aircraft, attack helicopters, cruise missiles, and unmanned aerial vehicles flying at low and extremely low altitudes. The system's versatility extends to engaging ground-based armored targets. It possesses the capacity to intercept targets traveling at both subsonic and supersonic speeds, irrespective of the time of day. Its effective range reaches up to 8 kilometers. While maintaining the familiar 35mm anti-aircraft guns, Sky Shield distinguishes itself from its precursor through the separation of its radar and control unit. According to its designers, this separation substantially enhances survivability. Notably, the control station can be positioned up to a distance of 500 meters from other system components. Furthermore, in a critical aspect, if the fire control system encounters a malfunction, the capability to independently search for targets is retained through the optoelectronic modules present on each launcher. Finally, there's Skynex, the unifying force behind this innovative array. Despite its name evoking thoughts of the Terminator series, Skynex is in reality a modular system designed to craft a tailored defense against prevailing threats. Serving as Rheinmetall's latest response to short-range air defense needs, Skynex employs the SkyMaster battle management system as its central intelligence hub. Flexible modularity characterizes Skynex, as it allows the integration of diverse sensors to suit specific mission requirements. Medium-range radars like the XTAR 3D Tactical Acquisition Radar offer target information, funneling it to the control node for processing within the SkyMaster network. The Oerlikon Revolver Gun Mark III and Oerlikon Twin Gun synergize with surface-to-air missiles, while adaptable provisions for active and passive electronic warfare, as well as future-proofing for high-powered lasers, cement its capabilities. Similar to other Sky systems, the unmanned revolver gun combines outstanding precision with formidable firepower. Boasting a firing rate of up to 1,000 rounds per minute, this 35mm cannon demonstrates a maximum aerial target range of 3,500 meters and 5,000 meters for terrestrial counterparts. Equipped with its dedicated sensor unit encompassing a tracking radar, TV and infrared camera, and laser rangefinders, the gun can seamlessly assume control from SkyMaster, autonomously tracking and engaging targets. The fundamental Skynex version is tailored to safeguard against an array of threats: aircraft, cruise missiles, tactical drones of varying sizes, air-to-ground missiles, as well as mortars and artillery rockets, all within distances of up to 4 kilometers. The deployment of Skynex to assist Ukraine in its conflict aligns with its capabilities. Skynex has been positioned as the optimal solution for safeguarding critical assets like airfields, military bases, harbors, bridges, and nuclear power plants from aerial strikes around the clock. These systems share striking similarities and can be effectively utilized in tandem to bolster defense against aerial threats. Being under the same company's ownership allows seamless integration of most of these systems. Their common thread lies in their impressive firing rates coupled with deadly accuracy. This reassures the owning military entities that the skies will be significantly safer. Additionally, the foresight in embedding future proofing within the latest systems is paramount as warfare continuously adapts to novel threats and countermeasures. All of these systems represent the cutting edge of military technology, and without a doubt, weapons like these will become more common on the battlefield in the not-too-distant future. The fact that the laser system is highly accurate, effective against modern weaponry, and relatively cheap to run means that it is an excellent alternative to traditional weapons. While Germany hasn't given up on its traditional machine gun, but has instead refined it further, its new fondness for laser technology will catapult it to greater heights in military weaponry. Expect to see many more of these systems in the arsenals of militaries across the world. The United States Navy is building a revolutionary aircraft carrier that could redefine naval power across the world's oceans. After the costly growing pains of the USS Gerald R. Ford, the Navy claims it has finally cracked the code. With refined electromagnetic aircraft launch systems, fully functional weapons elevators, and a Virginia payload module, Inspired Unmanned Warfare Center designed for large-scale drone operations, this new carrier promises sustained sortie rates and strike power that even near-peer adversaries may struggle to counter. How did the Navy turn Ford's failures into lessons learned? And what truly sets Enterprise apart from its troubled predecessor? Join us as we examine America's USS Enterprise CVN-80 that is making every Navy nervous. For decades, aircraft carriers have been America's ultimate show of force on the high seas. The Nimitz-class carriers did this job brilliantly for 3 decades, delivering 10 of these massive ships that kept America's enemies at bay. Then came the Ford class, meant to be the next evolution, the carrier of the future optimized for modern warfare. By 2025, the Navy had 11 carriers total, with 3 Ford-class ships either sailing, being built, or paid for. This fleet represents the most advanced carrier force on the planet. They do more than just look intimidating. They deter China from getting too aggressive in the Pacific. They keep American influence alive in every ocean. They show allies that America's technology is light years ahead. And most importantly, they give Washington the ability to hit back hard against anyone foolish enough to pick a fight. But here's where things got complicated. The first Ford-class carrier, the USS Gerald R. Ford, turned into an expensive nightmare that had Navy admirals pulling their hair out. Ford tried to revolutionize everything at once, cramming 23 brand new technologies into one ship. It was like upgrading every system in your house simultaneously and expecting nothing to go wrong. However, everything went wrong. The Electromagnetic Aircraft Launch System, or EMALS for short, was supposed to replace the old steam catapults that had been flinging jets off carriers since World War II. Cool idea, except it kept breaking down. It was designed to work 4,000 times between failures. Instead, it broke after just 600 launches, forcing flight operations to stop dead in their tracks during testing. Then there was the Advanced Arresting Gear, the system that catches planes when they land. It was supposed to last 16,500 cycles between breakdowns. Reality? 450 cycles. Pilots weren't exactly thrilled about landing on a carrier with sketchy arrest gear, but that wasn't even the last of the challenges they experienced with the Ford. Then came the issues with the weapons elevators. These electromagnetic lifts were supposed to haul bombs and missiles from deep storage up to the flight deck where jets get loaded up. The contract said all 11 elevators had to work before the Navy accepted delivery of the ship. When the Ford was commissioned, only 7 worked. The others took years of expensive fixes to get operational. Congress was furious. Costs ballooned $13 billion over budget, and everyone started asking the obvious question, was all this fancy new technology actually worth it? The Navy learned the hard way that they couldn't revolutionize everything at once. So when it came time to build Enterprise, they took a completely different approach. Instead of rushing to install experimental systems, they built dedicated test facilities on land. Engineers launched and recovered aircraft thousands of times, deliberately breaking components to figure out what failed and why. They redesigned weak points, upgraded problem parts, and tested everything again and again before installing anything on Enterprise. The construction schedule got longer, but Navy leaders decided that delays were better than delivering another broken ship. This time, political pressure to hit deadlines took a back seat to actually building something that worked. The lessons from Ford's disaster were expensive, but the Navy finally learned them. Enterprise got serious upgrades based on Ford's failures. The electromagnetic systems receive upgraded power components that could handle the electrical loads without frying themselves. Engineers replaced parts prone to burning out with more robust alternatives that had been tested through thousands of cycles. The weapons elevators got simplified designs, cutting out unnecessary complexity that caused Ford's elevators to jam and fail. Instead of experimental motor configurations, they used proven designs that actually worked. The installation timeline changed too. Rather than turning on all systems simultaneously and hoping for the best, Enterprise would activate systems one at a time. This methodical approach meant engineers could troubleshoot each system individually before adding more variables. It's like checking each ingredient while baking, instead of throwing everything together and wondering why your cake exploded. Enterprise's construction timeline shows just how seriously the Navy took these improvements. Steel cutting began in August 2017 at Newport News Shipbuilding in Virginia, the only place in America that can build nuclear-powered carriers. The keel got laid in April 2022, when the ship was about 13% complete. This formal ceremony marked the Navy's official commitment to construction milestones and delivery schedules. By November 2024, something remarkable happened. Shipbuilders floated Enterprise's mid-body section for the first time, moving it within the massive dry dock to make room for the next carrier, USS Doris Miller. This required flooding the dry dock with over 100 million gallons of water, carefully floating the partially built Enterprise, then repositioning it so work could continue on both carriers simultaneously. It marked the first time two Ford-class carriers were under construction in the same dry dock. The logistics alone were mind-boggling. Construction milestones kept coming. In March 2025, shipbuilders lifted the 940-ton aft section into place, a massive piece of the puzzle that required precision welding and exact dimensional alignment. But delivery dates kept slipping. First, the Navy targeted March 2028. Then material shortages pushed it to September 2029. Then suppliers couldn't deliver critical components on time, and the date slid to July 2030. Now let's get into the specs. This formidable beast will displace approximately 100,000 tons when fully loaded. That's the weight of about 50,000 cars floating on water. The ship stretches 333 meters long with a flight deck 78 meters wide. Basically, it's longer than 3 football fields and wider than most city streets. 2 A-1B nuclear reactors sit deep in the hull, providing essentially unlimited range. These reactors generate enough electrical power to run all the ship's systems, plus have massive reserves left over for future energy weapons and electromagnetic systems that the Navy hasn't even invented yet. The reactors will run for 20 to 25 years before needing refueling, and that only happens once during the ship's 50-year service life. This nuclear endurance creates strategic advantages that diesel-powered carriers simply cannot match. Enterprise can stay on station indefinitely without needing vulnerable tanker ships to bring fuel. Conventional carriers need regular refueling, which means support vessels that enemies can target. Enterprise, it just keeps going. The electromagnetic launch systems represent the most visible upgrade from old-school carriers. 4 EMALS catapults will smoothly accelerate aircraft from a dead stop to flying speed in about 3 seconds. Unlike steam catapults that jerk aircraft forward with brutal force, EMALS uses linear induction motors providing precise acceleration control. This means less stress on airframes, which means jets last longer. The system can launch everything from lightweight drones to fully loaded strike fighters carrying tons of weapons and fuel. Steam catapults struggled with this weight range, either being too gentle for heavy aircraft or too violent for light ones. EMALS adjusts the acceleration profile for each launch, like having a dimmer switch instead of just on-off. Early Ford operations proved EMALS could work, but reliability improvements for Enterprise address all those power failures and component burnouts that plagued Ford. The Navy wasn't taking chances this time. The advanced arresting gear catches landing aircraft using electromagnetic controls instead of hydraulic systems. This reduces the violent deceleration that slams pilots into their seats and strains airframes. Gentler recoveries mean longer aircraft service life and fewer structural repairs. For pilots who land on carriers for a living, anything that makes the experience less bone-rattling is a win. Now let's talk about those infamous weapons elevators. Enterprise will have 11 of these electromagnetic lifts designed to move bombs and missiles from storage magazines deep in the ship up to the flight deck where aircraft get armed. These elevators use linear electromagnetic motors instead of cables and pulleys, theoretically allowing faster munition transport with less maintenance. Theoretically. Ford's elevator development consumed years and millions of dollars because the complex electromagnetic controls were nightmares to integrate. Enterprise benefits from simplified designs and proven motor configurations, plus software fixes addressing everything that went wrong on Ford. The Navy spent $50 million just on Enterprise elevator improvements. That's how determined they were to avoid another elevator disaster. The Air Wing Enterprise represents cutting-edge American naval aviation. Expect approximately 75 to 90 aircraft depending on the mission, F/A-18E/F. Super Hornets provide the backbone. capable of attacking air and ground targets with equal effectiveness. F-35C, Lightning II, stealth fighters penetrate enemy defenses that would shred conventional aircraft, gathering intelligence with advanced sensors while dropping precision weapons on high-value targets. EEA-18G Growlers jam enemy radar and communications, essentially blinding adversaries and preventing them from coordinating responses. E-2D Advanced Hawkeye aircraft provide airborne early warning, detecting threats hundreds of miles away and coordinating the entire air wing's operations. MQ-25 Stingray drones extend strike ranges by refueling other aircraft mid-flight, reducing dependence on vulnerable tanker planes. But here's what really sets Enterprise apart. An unmanned aviation warfare center specifically designed for large-scale drone operations. This $50 million facility reflects the Navy's recognition that future carrier warfare will increasingly rely on unmanned platforms. Drones will conduct surveillance missions too dangerous for pilots. They'll strike defended targets where losing a human crew would be unacceptable. They'll perform electronic warfare and refueling missions while preserving expensive manned aircraft for missions requiring human judgment. The center provides dedicated spaces for drone maintenance, mission planning, and data analysis that current carriers completely lack. This represents a fundamental shift in thinking about carrier air wings. The future isn't purely manned aviation anymore. It's a mixed fleet where unmanned platforms handle the dirty, dangerous work, while human pilots focus on complex missions requiring split-second tactical decisions. The sensor and combat systems give Enterprise situational awareness capabilities beyond anything previous carriers possessed. The dual-band radar combines S-band and X-band arrays into one integrated system providing 360-degree coverage against air and surface threats. S-band radar detects targets at extreme ranges. X-band radar provides precise tracking and fire control solutions for engaging those threats. This integration enables simultaneous tracking of multiple targets, instant threat assessment, and coordinated engagement planning that previous radar systems couldn't achieve. The ship's self-defense system ties together all defensive weapons, including evolved Sea Sparrow missiles and rolling airframe missiles, creating layered defense against anti-ship missiles, aircraft, and surface threats trying to get close enough to hurt the carrier. Enterprise's construction carries implications far beyond American naval power. In November 2025, China commissioned the Fujian, their third aircraft carrier and the first non-American carrier featuring electromagnetic catapults. Displacing about 80,000 tons with 3 electromagnetic catapults and conventional diesel engines, Fujian represents China's most advanced carrier yet. It signals Beijing's determination to challenge American naval dominance in the Western Pacific. Sure, Fujian is smaller than Enterprise. It carries fewer aircraft. It lacks nuclear endurance and must refuel regularly. But those electromagnetic catapults demonstrate that China achieved technological parity in critical carrier systems. They figured out how to build what America builds. That's concerning. Delays in Enterprise's delivery will give China time to refine Fujian's systems and potentially build improved follow-on carriers incorporating lessons learned. Every month Enterprise sits incomplete is another month China uses to catch up. The competitive pressure is real. Russia adds complexity despite having limited resources for carrier construction. They operate one aging carrier, Admiral Kuznetsov, which breaks down constantly and spends more time in dock than at sea. Russian naval planners have proposed nuclear-powered carrier designs displacing up to 90,000 tons, representing substantial improvements. Budget constraints and shipyard limitations make Russian carrier construction unlikely soon, but the design concepts show Russia recognizes carriers remain relevant power projection tools. European allies watch Enterprise development closely while considering their own carrier needs. France operates the nuclear-powered Charles de Gaulle, displacing 42,000 tons, significantly smaller than American supercarriers, but still capable. The French Navy plans a replacement carrier incorporating electromagnetic catapults based on American technology, with construction potentially starting in the early 20s. The United Kingdom operates 2 Queen Elizabeth-class carriers, displacing 65,000 tons each. These use conventional propulsion and ski-jump launch systems, rather than catapults. While they demonstrate Allied commitment to carrier aviation, their smaller size and conventional power plants limit operational flexibility compared to American nuclear supercarriers. They're good ships, just not in the same league as Enterprise. Newport News Shipbuilding faces enormous challenges building Enterprise. It's the only American facility that can construct nuclear carriers, creating strategic vulnerability. If something catastrophic happened here, America's carrier construction capability would vanish overnight. The facility employed about 25,000 workers in 2025, but faced persistent workforce shortages. Training new shipbuilders takes 3 to 5 years for specialized skills like nuclear welding and reactor installation. It's quite impossible to just hire workers off the street for nuclear components. The training pipeline is long, meaning workforce expansion can't quickly fix production bottlenecks. Supply chain constraints made everything worse. Enterprise requires components from over 4,000 suppliers. Many produce specialized items exclusively for carriers. When suppliers hit delays, entire construction phases stop. This means attempts to accelerate construction often failed because critical components didn't exist and couldn't be manufactured faster regardless of funding. Cost control became a persistent headache. Enterprise received approximately $13 billion in funding through fiscal year 2026, with costs escalating as delivery dates slipped. The two-ship contract covering Enterprise and Doris Miller totaled about $18.5 billion in 2025, indicating per-ship costs approaching $9 billion. These costs substantially exceeded Nimitz-class carriers costing $4 to $5 billion each in equivalent dollars. Congressional oversight intensified, with legislators questioning whether electromagnetic systems justified the premium compared to proven Nimitz designs. Navy leadership defended costs by emphasizing life cycle savings. Electromagnetic catapults require less maintenance than steam systems, reducing crew sizes. Advanced reactors provide greater power with fewer operators. Weapons elevators enable faster rearming, supporting higher sortie rates. These arguments convinced some supporters but faced skepticism from critics noting Ford systems hadn't demonstrated promised reliability yet. Looking forward, Enterprise's completion will provide critical validation of Ford-class technologies. If Enterprise proves electromagnetic systems work reliably, if weapons elevators function properly, if the ship sustains high sortie rates during deployment, then the Ford-class program gets vindicated. But if Enterprise repeats Ford's struggles with system failures and extended maintenance, fundamental questions about the Ford-class concept will intensify. The stakes extend beyond Enterprise to encompass the entire planned program of 10 carriers representing several $100 billion and the foundation of American naval power through the 21st century. The geopolitical environment adds urgency. Chinese naval expansion continues at unprecedented pace, with analysts projecting 6 carriers by the mid-2030s, supported by modern destroyers and submarines. Russian naval modernization includes advanced submarines and anti-ship missiles threatening carriers near Russian territory. Iranian forces employ swarming tactics with small boats and mines that could threaten carriers in confined waters like the Strait of Hormuz. These threats create environments where American carriers must maintain technological advantages to offset numerical disadvantages. The name Enterprise carries tremendous weight. 8 previous ships bore this name. The legendary CV-6 distinguished itself throughout World War II, participating in virtually every major Pacific campaign and surviving despite horrific battle damage. The nuclear-powered CVN-65 served 51 years as the world's first nuclear carrier, setting endurance records proving nuclear propulsion worked for large warships. Naming CVN-80, Enterprise ensures the legacy continues, placing symbolic pressure on the ship to uphold its predecessor's distinguished records, while establishing new performance standards for the Ford-class program and American naval aviation. The commissioning ceremony in the early 2030s will mark both celebration and assessment. Olympic gold medalists Katie Ledecky and Simone Biles will sponsor the ship, representing American excellence. Navy leadership will declare Enterprise operational, but the true test comes during workup periods and deployment cycles, where the ship must prove that lessons from Ford's troubles translated into reliable systems and sustained performance. Crew quality of life improvements affect retention and effectiveness. Individual berthing replaces hot racking, where sailors shared bunks on rotating schedules. Enhanced gyms, recreation spaces, and internet connectivity help retain skilled personnel in competitive labor markets. These improvements pay dividends in personnel retention, operational readiness, and sustained performance during demanding deployment schedules. Enterprise represents more than metal, electronics, and nuclear reactors. The carrier embodies American commitment to maintaining naval superiority through technological innovation and sustained investment despite challenges. The delays and difficulties don't diminish the importance of ensuring America operates the world's most capable carrier fleet as foundation of naval power. As construction continues at Newport News, with the systems undergoing testing and as delivery approaches, the world's navies watch nervously. Assuming the program's remaining challenges are overcome, Enterprise will emerge as a new standard for aircraft carrier capability. Rival navies will be forced to reckon with a platform most cannot hope to match for decades. That enduring technological edge and operational flexibility will continue to anchor American naval power well into the 21st century. Dozens of contacts, all moving fast, all closing on the same point. That's what the radar picture looks like when an Iranian drone swarm is inbound. Not one threat, not two, but a wall of cheap flying machines coming from multiple directions at once, each one designed to make sure the ship in front of them runs out of ways to fight back. 5 years ago, that was a real problem with no clean answer. Today it isn't, because somewhere in that engagement, a beam of focused light starts working through the swarm one drone at a time, and the drones just stop flying. No warning, no explosion at range. They just fall. Iran built its entire naval harassment strategy around a vulnerability that no longer exists. And that's the story we're getting into right now. Why Iran built a drone swarm strategy in the first place. To understand why this matters, you have to start with Iran's actual military situation, because Iran didn't build a drone swarm strategy because it wanted to. It built one because it had no other choice. Iran can't fight the US Navy head-to-head. That's not an opinion, it's just arithmetic. A US carrier strike group carries more air power than most countries' entire air forces. Iran's surface fleet is aging, its air force runs on decades-old American hardware, it can no longer get parts for, and its Navy doesn't have the blue water capability to project force beyond the Gulf. Conventional confrontation with the US would end badly and quickly, so Iran went a different direction. Instead of trying to match American capability dollar for dollar, they built a strategy around volume and cost. Send enough cheap things at a problem, and eventually the problem runs out of expensive solutions. The Shahed series drones are the heart of that approach. They're not sophisticated. They fly slow, they're relatively easy to detect on radar, and they don't have the kind of electronics you'd find on a military aircraft. What they have is price. A Shahed 136 costs somewhere in the range of $20,000 to $50,000 to produce. A standard missile intercept costs over $2 million. Send 20 drones at a ship and force it to fire 20 missiles, and you've just burned through $40 million worth of the enemy's inventory for under $1 million of your own. That's a trade Iran wins every time. And the strategy had real teeth. In 2019, drone and cruise missile strikes hit the Saudi Aramco processing facilities at Abqaiq and Khurais, knocking out roughly 5% of global oil supply overnight. The attack, in which US officials linked to Iranian hardware, showed the world that this wasn't theory. Cheap aerial munitions could reach high-value targets and cause serious damage before anyone could stop them. In the Red Sea, Houthi forces backed by Iranian weapons and training ran the same playbook against commercial shipping and US Navy warships for months. The USS Carney alone fired over 100 interceptor missiles in a single deployment period, defending against drone and missile attacks. 100 missiles. Gone. At sea, you can't just reload. A ship carries what it carries, and once the magazine runs low, the options get thin fast. That's the vulnerability Iran was targeting. Not the armor, not the sensors, not the crew, the inventory. Western navies are built around expensive precision weapons that you can only carry so many of, and Iran was betting it could keep sending cheap drones until those weapons ran out. For a while, the bet looked reasonable. Then the US Navy started putting a very different kind of weapon on its ships. what the U.S. Navy's laser weapons actually are. The system the U.S. Navy has been quietly putting on its surface ships is called Helios, high-energy laser with integrated optical dazzler and surveillance. USS Preble was the first destroyer to receive it, making her the first operational U.S. surface combatant to carry a solid-state laser weapon. Not a prototype sitting in a lab, not a test rig on a barge, a combat-ready system mounted on a warship operating in real threat environments. The physics behind it are simpler than you might expect. Helios focuses a high-powered beam of light onto a target and holds it there. The energy transfers into the surface material as heat, and it keeps building until something fails. The airframe warps, the engine seizes, the fuel ignites, or the electronics fry. There's no warhead, no shrapnel, no projectile traveling downrange. Just a sustained column of thermal energy moving at the speed of light, delivered precisely where the fire control system points it. What that means in practical terms is a cost per shot figure that sounds made up until you look at how the system actually works. Each firing costs roughly $1 in electricity. That's it. Compare that to the missile intercept costs we already covered, and you start to see why the Pentagon kept pushing this program even when early versions underperformed. The magazine situation is what really separates this from every other weapon on the ship. As long as the ship's power generators are running, the laser can keep firing. There's no reload, no resupply run, no hard limit on engagements per sortie. In a prolonged drone harassment campaign, exactly the kind Iran has been running in the Gulf, that's not a minor advantage. It's a structural one. Helios also isn't a single-mode weapon. At lower power settings, the dazzler function can blind the optical sensors on a surveillance drone without destroying it. Useful when the rules of engagement require a measured response. Step up the power and you can disable propulsion systems or cook the electronics without the airframe coming apart. Go to full power and you're burning through the drone itself. The operator picks the effect, the system delivers it. Before Helios, the Navy was already fielding a lower power version called Odin, Optical Dazzling Interdictor, Navy. Odin went on multiple surface ships first, which gave the service real operational data on how directed energy performs outside a test range. Humidity, sea spray, atmospheric turbulence, all of it affects how a laser beam holds together over distance, and you can't simulate that in a lab. Odin gave the Navy years of that data before Helios ever went to sea. The limitations are real and worth stating plainly. Heavy rain or thick fog degrades beam quality significantly because the atmosphere scatters the energy before it reaches the target. The system also needs to hold its beam on a target for several seconds to achieve a kill, which means a target that's maneuvering hard at long range is harder to engage reliably. Against a supersonic anti-ship missile pulling high G turns, a laser at current power levels isn't your first line of defense. But slow, straight-flying drones on a fixed approach path? The dwell requirement barely matters. A Shahed flying a pre-programmed route at low altitude isn't doing anything to break the beam's lock. It's just flying in a straight line toward a ship that's now pointing something at it that doesn't miss and doesn't run out of ammunition. The encounter, laser versus drone swarm. Picture the scenario the U.S. Navy has been wargaming for years. A destroyer operating in the Persian Gulf, well inside the range corridor Iran uses for its drone operations. The radar picture fills with contacts. Not one or two, but a coordinated wave coming in from multiple bearings at once. Some are high, some are skimming low over the water to complicate the tracking picture. This is the swarm profile Iran has rehearsed, and it's specifically designed to split a ship's defensive attention across too many targets simultaneously. Against a traditional layered defense, this is where things get ugly fast. The Phalanx close-in weapons system can engage incoming threats, but it covers a limited arc, burns through its 20mm ammunition quickly, and by the time drones are close enough for Phalanx to reliably engage them, you're already in a bad position. Standard missiles are accurate, but as we covered, there aren't unlimited rounds on board, and they're wasted on a $20,000 drone. Electronic jamming works against drones that rely on GPS or radio command links, but Shahed-type systems fly pre-programmed routes, cut the signal, and they just keep going. None of the traditional answers solve the volume problem cleanly. Helios approaches the same problem differently. The fire control system pulls track data from the ship's radar, assigns priority to the targets posing the most immediate threat, and the beam slews onto the first contact. Slew, dwell, kill, move. The mechanical turret repositions fast enough that the transition between targets takes a fraction of a second. There's no reload cycle between engagements, no cooldown that a swarm operator could try to exploit. The system works through the contacts sequentially, and the engagement rate is measured in seconds per drone, not minutes. The actual kill mechanism depends on where the beam holds. On a drone with a combustion engine, sustained heat on the fuel system or exhaust components can trigger ignition. On an electric UAV, the beam cooking through the fuselage reaches the battery pack or motor controller, and that's the end of the flight. Either way, the drone doesn't explode dramatically at distance. It just stops flying and drops. Sometimes there's a small fire on the way down. Mostly it just falls. That last detail is something Iran's planners didn't fully account for, and it matters operationally. When a missile intercept happens, both sides know. There's a detonation, a debris field, a visible event that tells the attacking force its drone was stopped. The swarm operators can count intercepts, adjust, and keep pushing. With a laser kill, the feedback loop breaks down. A drone goes offline and the operators have no immediate way to know why. Signal failure, mechanical fault, or something they can't see burning through the airframe from 12 kilometers away. The swarm starts thinning, and the people who launched it don't have a clear picture of what's stopping it. U.S. Navy testing has demonstrated exactly this capability against drone targets under operational conditions, and the service has publicly confirmed Helios is deployed and functional. The Red Sea operations didn't just validate the threat picture, they put directed energy systems into a genuine combat environment for the first time, generating data on real-world performance that no test range can replicate. What Iran's operators would actually experience on the receiving end of a Helios engagement is a swarm that starts losing units with no obvious cause. No contrails, no explosion at range, no radio intercept of a missile launch command. Just drones going silent, one after another, while the ship they were sent to overwhelm keeps sailing. The swarm thins, the attack fails. And somewhere in an Iranian operations room, someone's trying to figure out what just happened to their strategy. What this means for Iran's strategy going forward. The math Iran built its doctrine on has flipped completely. A dollar defeating a $20,000 drone isn't a minor economic inconvenience. It's the entire logic of the swarm strategy running in reverse. Iran needed the cost exchange to work in its favor, and now it doesn't. So what does Iran do next? There are a few options on paper, and none of them are good. The first is speed. If a laser needs several seconds of dwell time to achieve a kill, then a faster drone reduces the window the beam has to work with. In theory, you could build drones that cross the engagement zone quickly enough to limit damage. In practice, faster drones cost more to produce, require better propulsion systems, and burn more fuel, which cuts range. The whole point of the Shahid approach was disposable cheapness. The moment you start engineering for laser resistance, you're spending more per unit, which means you need fewer of them, which means the swarm gets smaller, which means the saturation strategy stops working. Reflective coatings are the other idea that gets floated. Certain materials can deflect or disperse laser energy rather than absorbing it. So coat the drone's surface, and maybe you reduce the beam's effectiveness. The problem is that materials capable of reflecting the specific wavelengths, military lasers operate at add weight, add cost, and require manufacturing precision that a mass production drone facility isn't set up for. You've turned a cheap, expendable weapon into an expensive, specialized one. And you've still only bought a few extra seconds of dwell time, not immunity. The saturation angle is the only one with any real logic to it. If you can't make each drone harder to kill, send enough of them that the laser can't work through the whole swarm before some get through. To do that, you need to know the system's maximum engagement rate, how many drones per minute it can cycle through, and then exceed it by a wide enough margin that some survive. The engagement rate for Helios is not public information. Iran would be building toward a number it can't verify, spending money on drone production at a scale that starts to undermine the cost advantage that made the strategy viable in the first place. Every Iranian naval commander and IRGC planner operating in the Gulf now has to factor in that any U.S. Navy destroyer they're looking at might be carrying a weapon with an effectively unlimited magazine. That changes targeting calculus, risk tolerance, and the whole harassment playbook Iran has been running for years. There's an irony buried in all of this that's worth sitting with. Iran's persistent drone pressure in the Gulf and the Red Sea, the harassment, the Houthi campaigns, the cost exchange problem that had Western navies genuinely worried. That pressure is a big part of why the U.S. moved so fast to get directed energy systems operational. Iran kept poking at the vulnerability, and the U.S. responded by closing it. The aggression that was supposed to stress American naval capacity may have done more to accelerate American laser development than any Pentagon budget cycle would have on its own. Iran spent years building a strategy around a math problem it thought the U.S. couldn't afford to fix. Then the U.S. fixed it for roughly $1 a shot. China has missiles capable of sinking every American aircraft carrier in under 20 minutes. The Pentagon has confirmed it, and for years the United States Navy had no credible defense. Now America is testing a secret energy shield, a high-energy laser system designed to track and destroy missiles at the speed of light. Could this futuristic technology finally neutralize China's deadliest weapons before they strike? Join us as we uncover the details of the energy shield that the U.S. Navy is presently testing to neutralize China's threat. For 80 years, the aircraft carrier has been the ultimate symbol of American military power. No other nation has built them in the same numbers, operated them at the same scale, or projected force through them as effectively as the United States. At any given moment, the United States Navy operates 10 of these floating air bases, each one a city at sea, capable of launching dozens of combat aircraft over any ocean on the planet. They are the backbone of American foreign policy, the instrument through which Washington signals resolve, enforces no-fly zones, and responds to crises from the Persian Gulf to the South China Sea. And for decades, they were essentially untouchable. That is no longer true. China has spent 20 years building a specific category of weapon designed for one purpose: killing American aircraft carriers. And according to the Pentagon's own assessment, they have succeeded in creating an arsenal that represents a genuine existential threat to the most powerful naval platforms ever constructed. The threat has a name: hypersonic missiles, and China has more of them than anyone else on Earth. China now fields what the Pentagon itself describes as the world's leading hypersonic missile arsenal, a capability specifically tailored to target high-value naval assets, such as aircraft carriers. That is not the assessment of a think tank or a journalist. That is the American military acknowledging in its own official documents that a foreign adversary has built a weapon system specifically designed to destroy its most important platforms, and that adversary currently leads the world in that technology. To understand why this matters so much, you need to understand what makes a hypersonic missile fundamentally different from anything the United States Navy has ever faced before. A conventional cruise missile flies at subsonic or low supersonic speeds. It follows a relatively predictable flight path. The Navy's existing defense systems, radar arrays, interceptor missiles, close-in weapons were designed and refined over decades to track, predict, and destroy exactly these kinds of threats. The United States is very good at shooting down cruise missiles. The Red Sea operations against Houthi attacks prove that repeatedly. A hypersonic missile is a different category of problem entirely. Hypersonic weapons fly at between 5 and 10 times the speed of sound, and their ability to change course mid-flight makes them extraordinarily difficult to shoot down. They can fly as low as conventional aircraft while maneuvering on their way to the target, challenging defensive systems in ways that existing threats do not. The combination of extreme speed and mid-course maneuverability means that traditional intercept calculations, the mathematical models that tell a missile where an incoming threat will be when the interceptor arrives, simply do not work. By the time a defense system predicts where a hypersonic missile is going, the missile has already changed direction. The flagship of China's hypersonic arsenal is the DF-17. The DF-17 is a medium-range hypersonic missile that can be armed with a hypersonic glide vehicle and reportedly reach speeds of Mach 10, 10 times the speed of sound. while striking targets from more than 1,500 miles away. At that speed, covering 1,500 miles takes roughly 18 minutes. That is the timeline within which American Carrier Strike Group commanders would have to detect, track, classify, and destroy an incoming threat that is actively maneuvering to defeat any intercept attempt. Defense Secretary Pete Hegseth has stated plainly that 15 hypersonic missiles could destroy all 10 American aircraft carriers within the first 20 minutes of a conflict with China. The man running the Pentagon, making this assessment openly in a public interview, is effectively saying that the central instrument of American naval power is vulnerable to a volley of missiles that China can fire from the Chinese mainland. A leaked Pentagon brief cited by the New York Times reported that China has amassed an arsenal of around 600 hypersonic missiles capable of traveling at 5 times the speed of sound, while the United States had not yet deployed a single one of its own. 600 to 0. That is the hypersonic gap that the United States military is currently trying to close under enormous time pressure, with no margin for procurement delays or program management failures. The question that naturally follows is, what is America doing about it? The answer the Navy has been pursuing for years and is now accelerating with renewed urgency involves firing back not with missiles, but with light. Laser weapons. Directed energy systems that fire concentrated beams of energy at the speed of light itself, 300 million meters per second, and can in theory intercept any object that is moving slower than that, which is everything, including hypersonic missiles flying at Mach 10. The concept is not new. The United States military has been experimenting with shipboard laser weapons since the 1980s, with limited results. The history of directed energy research in the American military is littered with programs that showed enormous promise in laboratory conditions and then encountered brutal reality when exposed to the ocean environment. Salt air, humidity, rolling seas, power generation limitations, atmospheric distortion, and fell apart. Senior Navy leaders have been openly critical about the pace of progress. One Navy admiral publicly stated he was embarrassed at the state of the service's directed energy weapon developments. Another declared that the Navy must deliver on the promise that this technology offers. But something has shifted. The pace of testing has accelerated, the urgency is undeniable, and real results are beginning to emerge. In August 2022, the Navy installed Helios, the high-energy laser with integrated optical dazzler and surveillance system, on the Arleigh Burke-class destroyer USS Preble. Developed by Lockheed Martin, the 60-kilowatt system integrates directly with the ship's Aegis radar and combat system. Helios is not a science project mounted on a test barge somewhere in a quiet harbor. It is a permanent installation on an operational warship, integrated into the same combat management system the ship uses to fight every other threat in its threat library. In a 2025 demonstration, the Preble used Helios to shoot down 4 drones in a single engagement. 4 separate aerial targets engaged and destroyed by a beam of concentrated light fired from a destroyer sailing at sea. That is a meaningful operational milestone, not a controlled laboratory test with ideal conditions. But shooting down drones is not the same as stopping a hypersonic missile, and the gap between those two tasks is not incremental. It is a chasm. The Navy estimates that roughly 300 kilowatts of laser output would be needed to defeat anti-ship cruise missiles, 5 times the power of the current Helios system, and defeating a true hypersonic missile would require something in the range of 1 megawatt. To put that in perspective, 1 megawatt is enough electricity to power approximately 800 average American homes simultaneously. Generating that much power, storing it, managing the heat it produces, and directing it through a beam control system accurate enough to track a Mach 10 target, all on a ship rolling in open ocean, is one of the most demanding engineering challenges in the history of weapons development. This is the problem that Hellcat was created to solve. The high-energy laser counter anti-ship cruise missile program is specifically designed to expedite the development, experimentation, integration, and demonstration of critical technologies needed to defeat crossing anti-ship cruise missiles. Hellcat represents the Navy's recognition that Helios, for all its promise, is a first step and not a final answer. The program aims to produce and test a laser platform of over 300 kilowatts, a substantial leap from anything currently installed on an operational warship. In June of 2025, the Navy awarded Coherent Aerospace and Defense nearly $30 million to develop a new laser project called Songbo, tasked with advancing pulsed fiber lasers, wavefront control, and beam combination to realize a system targeting 400 kilowatts, built by integrating multiple 50-kilowatt modules. The modular approach is significant. Rather than trying to build one enormous laser generator, engineers are stacking smaller units whose beams are then combined into a single, more powerful output. It is the directed energy equivalent of combining many small streams into one powerful river. The Trump administration's December 2025 proposal for a new class of guided missile battleships called for 2 lasers on each ship, each with a beam power of between 300 and 600 kilowatts, power levels that could be capable of countering at least some categories of anti-ship cruise missiles. The fact that laser weapons are being designed into new ship classes from the keel up, rather than bolted on as afterthoughts to existing designs, signals that the Navy has made a fundamental decision. Directed energy is not an experiment anymore. It is a core element of future naval architecture. There is also a related concept that has received less public attention, but deserves to be mentioned here because it points toward the longer-term future of ship defense. Beyond lasers, researchers have explored the possibility of using ionized plasma, a superheated gas that carries electrical charge, to create fields that can disrupt the guidance systems and structural integrity of incoming threats. The United States Army has explored the concept of using dynamic pulse detonation technology to create plasma-based effects that could interfere with incoming threats, a concept that is reminiscent of science fiction, but is grounded in real physics research. The idea is that a pulse of superheated plasma could create a zone of disruption around a ship, interfering with the sensors, electronics, and structural materials of incoming missiles before a direct energy hit is even required. This research remains in its early stage, but it represents the frontier of where directed energy defense is headed over the coming decades. The stakes of getting this right are extraordinarily high. An aircraft carrier represents not just $13 billion in hardware. It represents the 5,000 sailors aboard, the 80 aircraft in its hangar, and the decades of training and operational experience embedded in every crew member. Losing a carrier in combat would be the most significant American military loss since the Second World War. It would reshape the global balance of power, shatter the perception of American invincibility, and hand China a psychological and strategic victory that no amount of subsequent military action could fully reverse. The USS Gerald R. Ford, the most advanced carrier ever built, is expected to serve well into the 2050s. But given the proliferation of weapons like the DF-17, it may be more vulnerable right now than any comparable platform has been in the last 80 years. That is the uncomfortable reality at the heart of this story. The most expensive and capable warship ever built is simultaneously the most threatened it has ever been. The laser program is America's bet that technology can outrun the threat. Whether that bet pays off in time is the central question of American naval security for the next decade. The testing results are promising. The engineering challenges are formidable, the timeline is urgent, and the adversary is not standing still. For the first time, the United States Navy unleashed a weapon that has made drug cartels tremble in the Pacific. Hidden for years under top-secret programs, the laser system Helios strikes faster than any missile and costs mere dollars per shot. Could this technology finally turn the tide against billion-dollar smuggling networks? And what shocking footage reveals the true power of lasers at sea? Will the cartels ever recover? Join us as we find out what happens when the United States Navy's laser weapons go to battle against the cartels. The USS Preble was cutting through the Pacific in October 2024, carrying a weapon no warship had ever tested in real-world conditions. Buried under layers of secrecy sat the Navy's new high-energy laser with integrated optical dazzler and surveillance system, known simply as Helios. This was not just another piece of military hardware. It was about to prove itself in action for the first time. Naval intelligence had been following strange activity near the California coast. Small, fast boats were moving drugs at night, And whenever Coast Guard cutters moved in, drones suddenly appeared overhead. These weren't amateurs trying their luck. Cartel groups had turned smuggling into coordinated military-style operations. Their speedboats could push past 60 miles an hour while carrying loads of cocaine worth more than $20 million. Meanwhile, the drones circling above provided real-time video to handlers on shore. The result was that the cartels always seemed one step ahead, making traditional interdictions nearly useless. That was about to change. With Helios on board, the Navy no longer had to waste $4.3 million Standard Missile-6 interceptors on drones that cost only a few $1,000s each. Instead, the laser system could fire at a cost of about $13 per shot. The weapon drew 120 kilowatts directly from the ship's own electrical system, removing the need to carry ammunition or resupply mid-mission. The way it works is both simple and extraordinary. Fiber optic cables generate separate beams of light that are combined into one powerful stream. This method, called spectral beam combining, produces temperatures hot enough to burn through a steel engine or set a drone's body ablaze in seconds. Unlike missiles or bullets that travel through the air, laser energy moves at the speed of light, 186,000 miles per second. Against cartel speedboats, this meant instant results. Many of the engines contained aluminum parts that vaporized under the heat. Crews often abandoned ship the moment they saw smoke rising from the stern. The drugs, however, stayed on board, making it easier for authorities to recover the evidence and cripple billion-dollar trafficking routes. The system tracks its targets through a mix of thermal sensors and radar. Unlike conventional weapons, it never runs out of ammunition. That made it particularly effective against the drone swarms the cartels had started using to overwhelm border patrols. What once required multiple ships and costly interceptors could now be handled in seconds by a single vessel equipped with Helios. There were limits, however. The weather along the Gulf Coast sometimes made things tricky. Heavy moisture in the air could scatter the beam, forcing operators to adjust power or wait for conditions to improve. Smugglers were quick to adapt, timing large-scale runs to coincide with storm seasons when laser weapons were less reliable. Even with these challenges, the Navy is already looking ahead. Plans are in motion to expand Helios to 300 kilowatts for use on future DDGX destroyers and next-generation frigates. Right now, only larger ships with advanced power systems can support the huge energy and cooling requirements. Smaller patrol boats, which would benefit greatly, simply don't have the infrastructure to carry the system yet. Helios is also linked to the Aegis combat system, giving ships layered defenses against both air and surface threats. Its optical dazzler offers another option. Instead of destroying a target, it can blind cameras and sensors. That allows intelligence officers to capture cartel data without losing the chance to analyze it. Military leaders see directed energy weapons like Helios as the next step in naval warfare. The cost advantage alone is significant, neutralizing cheap but numerous threats without draining budgets. More importantly, the system keeps crews safe and ensures the Navy maintains control over contested waters. The footage from that October mission remains under wraps, but the signal to cartels and other adversaries is unmistakable. While laser systems at sea reshaped how navies intercept smugglers and drones, the skies required an entirely different kind of breakthrough. The real question became, what happens when the world's most expensive bomber is paired with a weapon that costs less than a cup of coffee to fire? The Northrop Grumman B-2 Spirit, better known as the stealth bomber, carries a staggering price tag of about $2.1 billion per aircraft. Every mission burns through hundreds of thousands of dollars in fuel and support costs before the bomber even releases a single weapon. Conventional precision munitions only add to the expense. Air-to-ground missiles range anywhere from $100,000 to $4 million each. Military leaders started asking how long the United States could afford to fight drawn-out conflicts when opponents were fielding cheap drones and disposable hardware. That concern sparked a quiet but ambitious effort. Defense contractors began working laser technology into existing aircraft under classified upgrade programs. As part of its latest modernization, the B-2 Spirit received experimental laser pods designed to hit both ground targets and airborne threats. Instead of loading heavy racks of missiles or bombs, the system draws power directly from the plane's electrical generators. This cuts down payload weight and removes many of the limits imposed by conventional ordnance. The change in cost was staggering. Each laser shot came in at roughly $15. A bomber that once needed million-dollar cruise missiles to take out hardened targets could now destroy dozens for the cost of a single traditional warhead. For long campaigns against enemies with endless numbers but limited sophistication, the economics suddenly tilted sharply in America's favor. Adversaries, however, did not stand still. Many began deploying large swarms of cheap drones, launching them in the hundreds to overwhelm defenses. Conventional missile batteries quickly ran into a problem. Ammunition ran out fast, and each interceptor missile cost tens or even hundreds of thousands of dollars. Analysts calculated that, over time, enemies could bleed American defenses dry simply by throwing waves of expendable machines into the fight. Laser weapons erase that problem. Because they rely only on power from the aircraft, they can fire continuously without running out of ammunition. As long as the generators keep producing electricity, the beam can keep firing. In practical terms, this gave bombers something close to unlimited ammunition. Nuclear-powered ships and advanced electrical grids provided even greater endurance for extended operations. The combination of the B-2's stealth and its new directed energy weapons created a tactical edge no adversary had faced before. Radar operators might detect the bright streak of a missile launch, but laser strikes left almost no trace, only a brief flash of heat when the target was hit. That meant bombers could destroy multiple threats without giving away their position to nearby defenses. There were limits, of course. Lasers are still shaped by the environment. Dust, moisture, and rain scatter the energy beam and reduce its reach. Mission planners now include detailed weather forecasts in their operational checklists. On clear nights with dry air, the system is at its most lethal. This shift has already begun to influence how money is spent. Budgets that once poured into producing mountains of ammunition are being redirected into developing higher output lasers and more powerful generators to sustain them. The focus is moving from stockpiling shells and missiles to investing in renewable energy systems that can keep weapons firing as long as the plane remains airborne. Bomber crews are also being retrained. Unlike traditional bombs, lasers don't explode on impact. They require steady, precise contact with a target for several seconds. Pilots now practice flying patterns that hold beams on moving objects, while operators train on power management to make sure the weapons never drain the system during intense engagements. The shift represents more than just new technology. Strategists see it as a change in how wars will be fought and financed. Victory in modern conflict depends not only on advanced weapons, but also on the ability to fight for months or years without exhausting resources. With the B-2 Spirit now carrying directed energy systems, the United States military has shown that it is preparing for that future, one where cost-effective firepower and technological superiority go hand in hand. In the Red Sea, Iranian-backed forces discovered a profitable new market when Mexican cartels offered cryptocurrency in exchange for modern weapons. The Houthis, already armed with drones, guided munitions, and electronic warfare systems, found eager buyers in organizations flush with cash from fentanyl sales. With billions generated annually through drug trafficking, cartels could afford battlefield-proven equipment that American law enforcement had never faced at home. The trade was managed through encrypted networks overseen by Iranian Revolutionary Guard officers in Yemen. Cartels supplied chemical precursors for explosives, while in return they received completed drones, radar jammers, and even anti-ship missiles. These deals bypassed black market arms dealers and avoided international sanctions designed to stop dangerous weapons from spreading to non-state actors. By early 2024, Houthis were attacking United States Navy destroyers in the Red Sea with kamikaze drones and cruise missiles. Within months, similar systems surfaced along the Texas border. Border Patrol agents began to encounter drone swarms flying in formation, copying the same tactics seen overseas against commercial shipping. What had once been fast boat smuggling runs evolved into militarized campaigns. Cartels now fielded drones with thermal cameras for surveillance, jammers to cut police radios, and even explosive-laden suicide drones used against rivals. This level of sophistication posed a crisis that ordinary policing could not contain. Iranian advisors deepened the threat by training cartel fighters directly. In camps hidden across Mexico and Central America, Former Houthi drone operators taught everything from electronic warfare to coordinated strike tactics. These programs produced a new generation of cartel technicians who could build, maintain, and deploy weapons that rivaled those used in war zones. The network came to light when United States intelligence traced cryptocurrency movements, linking cartel accounts to Middle Eastern operators. Investigators matched payment schedules to known Houthi weapons purchases, proving that American drug demand was indirectly funding militants engaged in live combat with United States forces abroad. Soon, American police and border units began reporting weapons they had never seen outside of combat zones, night vision devices built for the battlefield, encrypted satellite communications, and armor-piercing ammunition. Local shootouts started to resemble clashes in foreign war zones, with gangs wielding tools meant to fight national militaries. Financial assessments confirmed the core problem. Cartels now commanded revenues greater than the defense budgets of many nations. With money on that scale, they could buy nearly any weapon on the global market. This economic power meant that criminal organizations inside the United States borders had the resources of a hostile state, turning a law enforcement challenge into a national security emergency. While Iranian weapons continued moving south through established channels, Mexican cartels were busy building something that caught intelligence agencies completely off guard. The pressing question became, what happens when criminal organizations begin producing military hardware faster than governments can track it? Using just the profits from a single fentanyl shipment valued at around $200 million, cartels set up underground aerospace manufacturing sites. These weren't makeshift workshops or hobbyist drone operations. They were full-scale facilities staffed with engineers who had once worked for legitimate defense contractors. Production lines inside disguised warehouses and abandoned mines were turning out as many as 50 advanced unmanned aerial vehicles every month, hidden from satellite detection by carefully built hangars and underground infrastructure. The Sinaloa cartel also managed to purchase 12 Turkish-made Bayraktar TB2 drones, aircraft already proven on battlefields in Ukraine and Syria. Instead of mounting explosives, cartel technicians reconfigured the payload bays to carry up to 500 pounds of compressed fentanyl. A single flight could deliver enough narcotics to saturate the East Coast drug market for half a year. The cartel's surveillance capacity transformed almost overnight. Persistent drone patrols equipped with thermal sensors and secure communication links provided constant updates on border patrol movements, high-altitude balloon locations, and law enforcement patrol patterns. Coordinated formations used artificial intelligence software originally designed for military swarm tactics, giving cartels real-time command over wide stretches of the border. Materials science also became part of their playbook. Factories began producing airframes out of carbon fiber and other advanced composites, giving drones more speed and endurance compared to aluminum-bodied aircraft. Many suppliers who sold the raw materials assumed they were dealing with ordinary commercial buyers and never questioned the unusual order volumes. Quality standards inside these underground factories rivaled those found in legitimate aerospace production lines. Cartel ingenuity extended into the seas as well. Narco submarines, once crude vessels for smuggling, evolved into autonomous carriers able to launch aerial drones while submerged. This created layered surveillance networks that existing interdiction methods could not detect, much less disrupt. Each submarine carried as many as 20 small drones, each with the endurance to remain airborne for more than 8 hours. Electronic warfare soon entered the picture. During clashes with rivals and law enforcement, cartels began deploying jammers and radar spoofing equipment. These systems disrupted police communications and even interfered with civilian aviation networks during smuggling runs. Much of the hardware and training came directly from Iranian sources, with instructors operating from bases in Central America. Autonomy made the threat even more dangerous. New targeting systems allowed drones to identify and pursue vehicles or people without any human operator in control. Facial recognition programs and vehicle matching algorithms enabled aircraft to track targets across state lines for days at a time. Police suddenly faced flying weapons that behaved more like hunter-killer machines than surveillance tools. By the early 2010s, the global drone market was worth an estimated $42 billion, and cartels were a part of it. Through front companies, they poured money into universities, startups, and artificial intelligence firms. Many researchers never realized their civilian projects were being adapted for cartel weapons programs. With mass production, costs plunged. Each combat-ready drone could be built for under $10,000. That meant a single drug shipment worth $50 million could finance as many as 5,000 drones. This direct link between narcotics profits and weapons development created exponential growth in cartel military strength. For the United States military, few options remained. Conventional airstrikes against these hidden factories risked heavy civilian casualties in densely populated areas. Strategic bombers armed with precision lasers emerged as the only realistic counter. Unlike explosive munitions, directed energy weapons could destroy underground entrances, manufacturing equipment, and command centers with surgical accuracy, carrying out strikes inside the United States territory without triggering the kind of devastation that traditional weapons would cause. Cartel breakthroughs in drone technology grabbed headlines, but America's investment in laser weapons gave the United States a clear advantage. Unlike missiles or conventional guns, directed energy systems have a major edge. They perform best in the very conditions that smugglers depend on. In many ways, nature itself has become an ally for the United States' defense. Could the very skies the cartels rely on actually be working against them? By 2023, military planners had figured out how to use weather and air conditions to know when lasers would work best. Some people pointed out possible limits, but in fact, these conditions usually gave the United States an advantage over the cartels. Clear skies, low humidity, and stable temperatures, the most common conditions along key border areas, allow lasers to strike targets with pinpoint accuracy, almost instantly. The deserts of Arizona and New Mexico tell a similar story. Cartels counted on heat to shield their drones, but the clear desert air helps lasers travel unimpeded. With minimal moisture or clouds, targets can be disabled long before they cross into United States territory. In this setting, dry landscapes became a natural ally for defense forces. Altitude works similarly. The higher a drone flies, the thinner the air becomes, meaning there's less to block or scatter the laser beam. This allows military lasers to stay tightly focused, deliver more energy to their target, and hit with devastating precision. Ironically, cartel drones trying to escape by flying higher only made them more visible to United States sensors, making it easier for operators to track, target, and disable them. The weather could pose a challenge. Fog, dust, heavy storms, or sudden rain showers can scatter light and slightly reduce a laser's effectiveness. Yet the United States systems are built to handle these obstacles. Satellites and radar provide real-time tracking, while conventional interceptors back up the lasers when nature tries to interfere. On most days, clear skies, dry air, and stable temperatures give American defenses a natural advantage. By the end of the day, the cartel's massive investments in drones rarely paid off. Instead of shielding them, the atmosphere often magnified the effectiveness of the United States' lasers. Sunlight, desert air, and thin, high-altitude conditions became silent allies, turning the sky into a vast, invisible extension of America's shield, a force the cartels could neither hide from nor fight. The cartels thought their drones and smuggling tricks gave them an advantage, but the United States Navy's laser weapon changed that. Quiet, accurate, and powerful, it turns the skies the cartels counted on into a place they can't control. After years of speculation, people around the world can finally see the United States Navy's laser weapon in action against cartel operations. For the first time, the power, speed, and precision of this technology are on full display. It shows how modern weapons can stop threats almost instantly without the need for traditional explosives or bullets. The lesson is clear. The future of fighting crime and warfare has arrived, and the balance of power has shifted in favor of those who can control the skies. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.